So we're ready, right? Okay, welcome everybody to the virtual seminar of the International Institute of Physics. It's a great pleasure to welcome today Claudio Chamon from Boston University. Claudio received his PhD from MIT, and after a postdoctoral appointment at the University of Illinois at Urbana-Champaign, he joined Boston University as a faculty in 1999. Claudio works with strongly correlated quantum matter and with out of equilibrium dynamics of classical and quantum systems. And he is very well known for us for his studies of the phenomenon of fractionalization in condensed matter systems with a prominent role of topology. The work of Claudio was highlighted by the American Physical Society and National Science Foundation in the US, and particularly he was elected a member, a fellow of the American Physical Society in 2008. So today, Claudio will tell us about classical and quantum circuits and about quantum statistical mechanics of encryption. Thank you very much, Claudio, for accepting our invitation and for being with us today. And I pass the word to you.
Okay, thank you, Dimitri, and everybody for the invitation. It's a pleasure. So I'm going to talk about the quantum statistical mechanics of encryption, and in particular, reaching the speed limit of ciphers, and we'll see that there is a connection about also how better to scramble even in the black hole. Somehow I cannot move. Oh, yeah. So we're going to be talking about fast scrambling, and here we're going to have like two sides. There will be an applied side, and there will be a fundamental side. And even though the fundamental side started by inspiring the applied side, I think what's interesting here is that the applied side will also have something new to say on the fundamental side. So on the applied side, we wanted to ask the question: can one encrypt with reversible classical circuits of depth log n, where n is the number of variables, the number of bits? And the importance of the question is that if yes, then we will construct a physics-inspired polynomial algorithm to compute directly on encrypted data without first having to decrypt it. So this is it's an important applied problem, and we'll talk more about implications. But at the same time, if we can do this, then we can go here to the fundamental side and ask the question: can quantum circuits scramble as fast, but better, and better in the sense of cryptographic requirements than a black hole? Because we know black holes can scramble fast. The question is that do they scramble well to that degree? So here, let's start with this notion of what the fast scrambler is. So a few years ago, starting with some work by Hayden and Praskil, that wanted to study the rate of information retrieval from evaporating black holes. They start to make this connection with quantum information. And then shortly after, Sekino and Susskind, they have this paper entitled Fast Scramblers, where they conjectured that the most rapid scramblers take time logarithm in the number of degrees of freedom in the system, that matrix quantum mechanics saturate the bound, and that black holes are the fastest scramblers in nature. So these were conjectures that then later, over the course of a decade, they were looked at in different ways. So let's get some sense as to why this log of n appears. So even before one can scramble, to even start talking about scrambling, one has to make sure that the information propagates over the whole system. So if you take a system, after time t, and if you assume that the propagation of information is ballistic, right, it propagates with a constant speed, for example, the speed of light. After time t, the radius is going to scale like t. Let me ask a question. Can you see the mouse?
Yes, we can perfectly
All
see
right.
it.
So the volume or the number of degrees of freedom reached will scale as r to the d. And then if you invert this relation and ask how long does it take, how much time for all the degrees of freedom to be engulfed by the kind of the light, then it would scale as n to the power 1 over d. And in particular, if you take g going to infinity, this power law becomes a log. And one noticeable thing here is that even if the propagation were diffusive, if you change the exponent of how r grows with t, in the infinite d limit, you will still get a log. So if there are reasons to believe that inside the black hole, you have this long-range connectivity, then you would get this log n, and this is the minimum bound. Then there were these connections drawn to unitary quantum circuits within qubits in the parallel studies of the idea of T designs. And what exactly were those studies? That, if you take a quantum circuit, and here we're gonna see this picture quite a few times in the talk. Suppose you have an input state, and this is the input side, and this is the output side of the computation. And these are the qubit lines. And then you apply gates, small gates, in this case here, acting only on 2 qubits. So you draw them randomly out of the set of unitaries belonging to U4, acting on only 2 qubits. And then at the end of the computation, you have the output state given by the unitary, which is composed of these small unitaries. And one question is how deep the circuit has to be in such a way that if you compute, for example, you take the density matrix or compute correlation functions, that multi-point correlation functions that you would compute because of this unitary generated by the circuit could not be distinguished from a random unitary belonging to the space of in U2 to the n. So this would be the scrambling by quantum circuits. And here we drew these circuits as little brick walls that I would think that this is 1G, like you only connect qubits, they're neighbors, and you alternate your layers of bricks. So this is a one-dimensional setup. But if you have long-range gates, then the idea and what's shown in these papers that one could scramble in log n depth if you're allowed to connect qubits far apart. It's still 2 qubit gates, but far apart. Now, one of the ideas that helps us understand these scrambling is the sensitivity to changing the input just a little bit. So, this is a quantum system, so it's not, chaos is not measured by, deforming the input wave function a little bit, but instead by, you can see the effect of the action of a certain operator at the input and how that propagates to the output. So imagine you take 1 qubit and you apply a Pauli sigma x operator to this qubit. So you flip it. Then on the input side, this is your new input state. And you can compute what the output state is. Here we just insert an identity, right? U dagger U. So you can take the old output state and see what is the effect of flipping that 1 qubit at input on the output. So the effect is going to be given by the evolved qubit flip. So it's basically the Heisenberg sigma x at site I as at tau being the time at the output. And this operator, will grow So the initial sigma x, if you compute the time evolution and you write in the basis of polystrings, the basis of operators, you can decompose any operator as a product of sigma x, sigma y, sigma z. And here, for convenience, we're gonna not write sigma y's, we're just gonna write strings of sigma z's and sigma x's. But this evolved operator will be a superposition of many, many, many polystrings, and strings of a large size, meaning that they will touch many of the qubits. So it's this operator spreading that tells us that the action of flipping something really propagates to the system and really change the output state. So that's a cartoon picture of the effect of kind of this chaotic behavior of flipping one spin and looking at what happens at the output. This constructing these so-called out-of-time order correlations, which were actually used in condensed matter by Larkin and et al. Many, many years before. But the basic idea is to look at a correlator that will tell the propagation by, for example, here, if you look at this commutator of sigma x at time 0 and a sigma z at time tau, and look at it as a function of tau and the distance between I and j. So for example, if I and j, say tau is 0 and I and j are at space-like separations, this commutator will be 0. The operators don't communicate. But then for any fixed I and j, after enough time, the commutator would no longer be 0. And it's actually more enlightening to write this commutator to just expand this expression and write it in terms of these. And this is the one that we call the out-of-time order correlation, because the times at which they appear are not natural when you do quantum field theory, because quantum field theory usually have either time order or reverse time order or contour order, like in the Schwinger contour, but they are ordered. And here they are out because you first have t, then 0, back to t, back to 0. So these correlators, they will vanish at large times, and then this quantity C will be maximized. But we'll focus on things like these OTOs. Now, the cartoon, basically translates like everything that's happening here. So you can think about this as you evolve the state, right? Imagine you have a state or an operator. You evolve to time t, so you evolve under the unitary. Oops. And then at time t, or tau, you measure sigma z, and then you come back to time 0, where you're gonna flip the spin, and then you go back, evolve it again by time t, apply sigma z again, and then you come back, and you flip it, and then you complete the trace. So these out-of-time order correlations are sequences of operators at 2 different times, and you go back and forth, with using your daggers, right? Until you complete the trip and you close the trace. Now, so this is the formulation, and these out-of-time order correlations that will go to 0 at long times, and they will go to 0 fast in the case of in the case of a black hole, in the case of the random quantum circuit, in time with the long range conductivity in time logarithmically in the number of qubits or the size of the black hole. Now, but some safety advice is that don't go near black holes, because bad things can happen to you. You can be stretched. The gravitational fields are very high. So that's the kind of advice I would expect our mothers to give us, but they don't worry too much about anybody going near a black hole, because if you take a bus, you probably cannot afford the bus fare to the center of the galaxy. But the kind of advice that we do, all of us heard in one form or another, is that don't accept candy from strangers. Like if you're sitting on the bus and there's somebody sitting next to you, don't accept candy from a stranger. Now, things are even more complicated to parents these days, because it's not just a stranger that sits on the bus, that sit next to one, but it's the whole World Wide Web, right? It's the whole internet. And that brings questions like, and this is taken from an article about a year and a half ago from the BBC. Should encryption be curbed to combat child abuse? And if you see, the headline was phrased as a question, because clearly it's something we want to do, combat child abuse, but also encryption. It is. The question is, if you remove it, you remove also, for example, dissent in some authoritarian regimes that would have access to everything that is exchanged by the citizens of the place. So it is a balance. But in the article, it's brought up that one of the ways that you can do both, right? You can keep privacy and you can combat abuse, is through homomorphic encryption, which is a form of encryption that lets users perform computations on encrypted data without decrypting. So you keep the privacy, but you could do, for example, machine learning on images and on text and exchanges, and tag it as dangerous or not without decrypting. Okay, so the applied side of what we're trying is to propose a physics-inspired alternative to homomorphic encryption, which, despite years and years of progress, it's still extremely slow. There's a huge overhead. So what we proposed, and that was the motivation to search for these fast ciphers, was the idea of encrypted operator computing. So we are physicists, so we think about computation as operation, especially after so many years of quantum computing. But everything here, you should be thinking about a classical computing, but classical reversible computing. So suppose you have some data, some message X, and it's encrypted through some function, some permutation, E of X. We can think about the action of this function, if it's a reversible function, an invertible function, as the action of an operator on a state X. Now, to compute an encrypted data would be equivalent to decrypt with the inverse of our invertible function E, apply the function F like we do in quantum computing, right, with all the qubits, and apply E again. So at the output, we would have E of F of X, because the E inverse will cancel this E, you apply F, and then you E again. Now, of course, this cannot be the end of it, because if you just concatenate your circuits, you can slice it here and get the decryption, right? So what one has to do is actually obfuscate this. Obfuscate is a technical, word in computer science for this, scrambling the circuit. So if you wish, there is a lot of studies in quantum information and in black hole physics about scrambling states. But here we're asking something different. We're asking, can we scramble the computation? Can we scramble the circuit? Now, it is possible. What makes it, what complicates matters is that gates are operators and not necessarily they commute. And because they don't commute, when we do this process of obfuscation, which is basically conjugation of gates, what happens is that the circuit gets longer. And it gets longer by some factor. And if you do it, layer by layer of the E's, and the layer is like a measure of time, the depth of the circuit time. So if it grows exponentially in L, the only way that you keep this overhead polynomial is if you could encrypt with log n layers. So now we're asking a question that can one actually encrypt that fast? And we borrow inspiration from the random quantum circuits and the black holes to know that, okay, this is possible, this is the limit. But if we can attain this limit, we could do this encrypted operator computing. So this is the motivation, but I need to come back to this question. Are there ciphers with login layers? So we're gonna work on reaching the limit of the shortest cipher. And we should expect that, one cannot encrypt faster than, you can scramble in a black hole. So it's going to be as fast as a black hole, but we'll see that we can actually do a more thorough, we scramble to a higher degrees than we've been asking of the black hole. So let me introduce the language here of, reversible classical circuits. And it's very much, you can think of it's exactly the same things that we use in quantum computing. It's just that our input states we're usually going to get as a state in the computational basis, some x, some n-bit number. So it's always a product state. And the gates, instead of taking gates out of unitary set, like, U4, we're going to take gates, 3-bit gates. That's a big difference. We need 3-bit gates to do universal classical computing. And they're going to be taken out of a different group, the group of permutations, SH, because you have 2 to the 3 inputs, and the reversible computation, you just take all those possible inputs and you invert them as a state. Sorry, you permute them as a state. So it's 8 in, 8 out, so it's in group SH. And then when you put these bricks together, we're going to generate a bigger permutation, right? And we can always think about this as a reversible computation, is that the output is the P of X. This is, again, in the computational basis, it's just one state, is a sequence of zeros and ones. But that you can write as an operator, because these gates here they belong to a group and they are an operation, just like in quantum computing. Indeed, actually, these gates, you can always break them into knots, CNOTs, and Toffoli gates, which are, and the Toffoli gate is universal for classical computation. This is a result that, if reversible computing on, it dates to the 80s with the Toffoli, Fradkin. But actually, it's notable that even a decade earlier, the result that you could do any, most classical computations using these little permutation boxes was known to Coppersmith and Grossman, that they showed that you can write any element of the alternating group, which is just a group of even permutations, right? So about half of your permutations you can write with these bricks. And to write the odd ones, you would need the equivalent of kind of a super Toffoli that touches all the bit lines. But you can do pretty much anything you want, especially if you put on syllabits. But so these groups generate the whole permutation group. Now, permutations are ciphers. So the idea is that you take an input state in this 2 to the n space of inputs, and you get another state, a different state. And encryption by block ciphers is exactly that. You permute the input state so that nobody knows what your message is, because you just throw it in some, ideally something that it's a random permutation. Now, as an example, the advanced encryption standard, which is the current NIST standard for this symmetric permutation encryption, it is a permutation. It does exactly something like this. It doesn't use these little boxes. It has another scheme, but at the end of the day, it is a permutation, and therefore could be broken down as a reversible computation. And here, what we want to do is take these ideas from quantum computing, right? And draw a random circuit where the key is basically, if you tell me which bits are wired and what is the gate that we use, the key is the circuit itself. And then the question is, how deep can they be and to be good scramblers? Now, about the wiring, well, wiring is where the physics of dimensionality comes in. So here we're looking at the top, say that time is on the perpendicular to the plane of the paper. And this is the position X. So if we only apply, and this I drew for qubits, so that's easier, we only have 2. If you only have gates between consecutive qubits, and then you alternate, how you connect them, you have a one-dimensional connectivity, okay? If you lay your qubits on 2 dimensions and put your bricks, between consecutive, and then you can put like the ones that are horizontal and then the ones that are vertical in a different layer, you have a 2-dimensional connectivity, or you can connect them at arbitrary large distance. That would be the g equals infinity. So the one thing we know is that if you remember, we had to go to g equals infinity to get to the log, and we'll do that too. But without the talk, when I draw the circuits, I choose to draw them like this because it's easier to draw. So if I go back and we're drawing like a 1D, but we'll keep in mind that we want these branching trees for the connectivity. We'll get there. Now, notation. So even though this is all classical computation, because we know that we can frame it in the same way as quantum computing or reversible computing, we can define the operators that flip a bit. For example, that measure a bit, sigma iz. If I apply to this bit string, I get -1 to the xi. So I either get an eigenvalue plus or -1 if the bit is 0 or 1. And I can flip a bit. I can flip bit I by negating this bit. So I have these actions of negating and measuring a bit. And for example, if I want to measure a bit at the output, what I would do is I take my input state X, evolve it with P, measure it, so they would get the -1 pi to the X, and then I will evolve it back so that they can get back the state X. Okay? And then we can think about the measurements at the output as basically the kind of the Heisenberg evolution, but not with a unitary, but with a permutation, which is also a unitary. And now we can talk about digital chaos, that a good cipher would be something that if you take some input that and so which leads to some output after you pass through the permutation P. If you flip a bit, you want to flip half of these bits here, or you want to flip all of them with probability of half, right? So you want this avalanche that you flip one and everything flips. So this is a chaos in the sense of, if you take the operator sigma x, it will evolve at the output, right, as something that flips many spins. So we want some kind of large Pauli string of flips. And the question you have is, what is the shortest circuit which can not, such a way that this permutation cannot be distinguished from random with a polynomial effort. So if I do a sequence of flips and measurements, can I tell if this thing is not random, right? So let's bring back those OTOCs that were used for the black hole studies, right? And here, there is something called the avalanche effect for a cipher, which is a measure. It's not, we'll see that we need many more things. We need basically all OTOCs, not just one. But this is the easy one to connect. So what this avalanche effect is that you flip a bit and you want to see how many flip. So you can, and this is the correlation that in the kind of a crypto community, they would write, is the sum over all input states, like an average over input states. You take the output bit j of the permutation of your output state, and you compare mod 2, it's an XOR, you compare mod 2, to the output with where you take one bit, say bit I, and you flip it. So in this notation, you XOR with the 2 to the I. So you compare for all x's the output with the input bit flipped. If they're equal, this adds to 0, and then you get a 1. If they're different, you get a -1. So this quantity will tell you, it will be a measure of the probability of flipping. So here, what we did is that we look at this and say, okay, this is an OTOC in disguise, okay? And it's exactly the same OTOC that we had looked before. You take a state X, and then this state, you're gonna measure the bit, right, at time tau. That's gonna be the equivalent of the -1 to this PJ here. You move it back to 0, right? You flip it, that's this guy. And then you go back to the output boundary. You measure it again, right? That's this thing. And you go back. So this correlator is written, it's basically this in our quantum language. And the sum over all states is basically the trace with an infinite temperature density matrix. So it's the same, it's that same OTOC that we saw before, and it's the same diagram here. So we're going to use this one, the OTOC, as a measure of the quality. Now, let me give an example of what a bad cipher would be, a simple one. If the circuit is linear, then this function, P of x plus C, is equal to P of x plus P of C plus a constant. In which case, when you add mod 2, the P of x will cancel this x here. So there's no x dependence. So if there's no x dependence, and this thing is either a constant plus or -1, so when I sum over all x's and divide, I will get my sec will be either +1 or -1. So clearly it didn't decay. And now if you average over circuits, you're still gonna get 0, but that's a bad thing to do. So what we'll do when we is often we're gonna take this correlator and we're gonna square before we average, like an Edwards-Anderson order parameter in the case of studies of classes, and that would get rid of this sign. But this is an example of something bad. And again, we go back to the same quantity that we translated the language of cryptanalysis into the language of physics. Just to give an example, okay, there are more complicated OTOCs that you could write, that you measure in the input, you measure in the output after evolution, and you come back and you flip, and you do this thing many times. This is just an example of something that we translated from an attack to this type of cipher. A tree, that there is an attack, but we can write it as an OTOC, and this is basically the upshot, that we can translate these things to OTOCs. But now we're going to come to a question that's really going to be, okay, what is new and different from what we already know from random quantum circuits and black holes? So the OTOCs must vanish, okay, to be a good cipher. But, okay, so it has to go to 0. But then the next question is, what is 0? Okay. Well, is this thing going to vanish? 0 is 0. If I multiply 0 by anything, I get 0. So that's not what we mean when we ask that the OTOC vanish. It vanished to some epsilon, right? Now, the next question is epsilon independent of the system size, or should be dependent on system size? Well, if we just ask that it vanishes, say as a power of the system size, 1 over n squared, and then in the thermodynamic limit, you say, yes, it goes to 0. But here's the problem, and this is why we actually have something different and a higher standard than what we ask for the black holes, is that if you want a good cipher is secure against a polynomial number of attacks, and if you think about this OTOC, you cannot average over all possible 2 to the n inputs. Imagine n is like 128 or 256 bits. You cannot do 2 to the 128, it's too costly, but you can sample over x's. And by sampling over X, you construct a distribution, right? And then this distribution, it gets narrower with 1 over square root of m, the number of measurements that you do. So if this thing is not exactly 0, right? You can just do enough measurements that your Gaussian will bracket, the average, and you see that it's, many standard deviations away from 0. So then, okay, so if this is a power law in n, you just need to do an m that is a power law in n, and you would be able to tell that it's not quite 0. So you distinguish it from a random permutation, a pseudo-random permutation. So what we're asking here to meet the cryptographic standard is that the OTOCs have to vanish to an exponential precision, not polynomial in n. Because you keep in mind that n is like of order, hundreds, right? It's not order, 10 to the 23. So we're really asking that we have to devise a means to kill these OTOCs in log n times. So we have a more strict criterion. In a way, and we'll come back to this, we will demand that it's not just the system is chaotic that has positive Lyapunov exponents, but we actually will require that they have infinite Lyapunov exponents. So then in the process, let's continue setting up the language. So any general plain text, ciphertext attacks can be written in terms of Pauli strings. So the generic, so it's an OTOC of where you apply operators 1,000 zeros in a number of them. Here in this example, k of them. The Pauli strings are written as products of sigma z's and sigma x's. Okay, so we don't use a sigma y because a sigma y can be written as sigma x and sigma z. So there are 4 to the n different Pauli strings, because for each site k, you have a choice of whether you're going to have a sigma z there or not and a sigma x there or not. Another way to count is just that you can have identity sigma x, y, or z. So every site you have 4 possibilities. There's a string weight, which is basically how many sites do you have sigmas, or how many sites you don't have identities. Also, you can define like how many of these sites you have sigma y's. Now, in the evolution with the permutation p, these strings evolve, and you can define like a string wave function, because given an initial state beta, after evolution with after you conjugate with p, you can basically expand in the basis of Pauli strings, and you can think about this as a wave function. And I will introduce this language of the string wave functions just because it gives us some intuition of what will happen as you evolve a string. So you have the string operator to state correspondence because you can assign string states alpha, and these alphas and betas just tells you like in the string where you have sigma x's or sigma z's, right? It basically tell you like which Paulis you have at each site. There is an inner product that you inherit from the trace of the string of Paulis. You can define an evolution associated with this permutation P. And so you have unitaries that evolve your string states. Your string states are normalized, and you even have there's some symmetry that I'm not gonna dwell on that. But the key point here is that the evolution of the string, you can think about as a string wave function, the amplitudes in front of each string. And then we go that if you want to write an arbitrary OTOC, and then you go to the Pauli basis of the strings, all these correlation functions are moments of the string wave function that and And imagine that time t equals 0, you start with a single string, and after you pass through your permutation, you conjugate it with your p. This string will delocalize. This wave function will be spread all over. What you want to resemble a random permutation or a random unitary, if we're dealing with unitaries, is that the string wave function looks like a random wave function in that space. So the first thing that the random wave function, a wave function has to do to become random is first of all is to spread out over the whole space, the whole Hilbert space of these strings. So measures of delocalization are, we usually use these inverse participation ratios as measures of wave function delocalization. And they're just moments of the wave function square. And you can define entropies associated with them. So one criterion for for all these, it's necessary that if your wave function is going to be random, it's necessary that first that all these entropies become maximal. Now, let me discuss first equilibrium and then dynamics. By equilibrium, I mean, if I go back to random permutations or random unitaries, what would these string entropies look like if I take evolution by a random unitary, or in other words, like if I take a random wave function in Pauli space? So let me start with we did this calculation, and then for the different classes, if I use random unitaries or random orthogonal transformations and the random permutations that we're interested in for ciphers. The random unitary is the easiest, and we can compute what is the probability distribution for the string amplitudes. It is basically, well, if it's a random unitary, those probabilities are going to become Gaussian with a certain standard deviation that's given by the dimension of string space. And you have only one constraint, that this wave function is normalized. So that pretty much fixes the prefactor here. And for all of these, what we find is that all these different entropies for different Qs, they're like Rayleigh in a way, but they're not entanglement, they're like string entropies. They're all, the maximum is in log 4, but there is a correction. There is an order 1 correction. Just like in the page limit, there is an order 1 correction to these entropies. And we can compute these order 1 corrections for all the ensembles, the unitary, the orthogonal, and we can calculate this distribution. So we also calculate for the permutations. The permutation is actually quite more work, but the amplitudes now are kind of quantized. They cannot just take any real value. They are quantized in units of square root of d. They're given by some Bessel functions, but still, we managed to compute what is the equilibrium entropy if you have a random permutation, and exactly what this correction. So this correction is important because we're now going to apply this to different systems and see if indeed we reach this maximal entropy with its kind of a page-like correction. So we introduce a lot of language, but let's apply it. And so the intermezzo here is an application to Feistel ciphers. So Feistel ciphers are one simple type of ciphers that you take your n bits and you break them into the L register and the right register. You just split evenly, half and half. And you have rounds in a recursion relation. And for each step in the recursion, what you do is you take whatever is on the right side and you move it to the left for the next level. And you take whatever was on the left and you add with a random function of what's in the right. And then you get the next round and you repeat it. And there's a repeat, an inverse function. This is a classic result in crypto by Luby and Rakov that they show that if one has access to pseudo-random functions like these, you can construct pseudo-random permutations. And their result is that if you do 3 rounds, they're pseudo-random, they cannot be distinguished from random. If you only look from the input side, the plain text side. And if you do 4 rounds, even if you can ask for the inverse permutations, you cannot distinguish. You put this thing in a black box and you really cannot tell whether you have a random a random permutation or if you have 4 rounds of this game here. Now, from the string perspective, we'd like the OTOCs to vanish and the entropy to saturate. So what we will do is like we'll play with this. And so we take different system sizes and we just implement exactly that for, a number of inputs and, well, here the entropy we actually use for all inputs. And we plot the entropy, the S1, the usual, P log P, as a function of the number of rounds. And this is the kind of plot that we've seen many, many times in the studies of random circuits when you talk about different kinds of entropy, entanglement entropy, how it saturates as a function of time. And here we've seen the same behavior that we saturate, after, well, small systems is hard to see that you saturate, but you see that it's getting better and better when you get to 4. Now, even more interesting is that if I take that theoretical calculation of the equilibrium, right, the maximum including the order 1 correction, and I subtract and I see, okay, what is the excess entropy? And you plot this for different system sizes. Now this is starting to look like what we do in StatMac when we do finite size scaling, right? That's how we identify that there is something. There's like if I look at this as a statistical mechanism, right? I would think, okay, this crossing point signaling there is a phase transition. And in finite size scaling, to the left of the transition, things are scaling one direction. And to the right, they're scaling in the opposite direction. This is kind of like it would be the fixed point that different system sizes will always be at this level. And this level is an order 1 correction. Now, this is that marginal case, right? And remember their result, because you can only look at integer rounds, is that you'd say this cannot be distinguished from a random permutation. But now I'm using physics tools and without knowing much about the proof or anything, but I look at just the entropy. And if I continue with my finite size scaling and I plot the correction as a function of n, I see that this correction is going exponentially to 0 with n. Now, we cannot do this calculation for n equals 100. And this is actually interesting, is that by talking to people in the cryptanalysis community, it's not so common. Actually, they doubt these ideas because it's not as common as in physics, right? We live off a finite size scaling because we know that we're not going to study systems of size 10 to the 20. So we identify transitions by knowing that if you have a scaling law, if you know the behavior of small n's, you can extrapolate to what happens in large n's. And I think this is an example, and it's an example of some of our tools applied to these other problems. And even if I didn't know anything about the results, I could already understand the phenomenology that there is something happening at 3 rounds, and at 4 rounds, you basically maximize the entropy in the large n limit. So that intermezzo was just to say that, well, we check these ideas and they hold water. Okay, we can understand those results in this language. But now let's talk about dynamics. Okay, how does the string wave function will delocalize and randomize. So what happens here is that when you apply these gates, gate by gate, there is a transition matrix element in string space for your Pauli strings to go from alpha to alpha prime. And we can compute these if we know the gate, the operator, and we can just compute these matrix elements. For every gate, there is a normalization for these transition matrix elements. And even though we're interested in the group S8 for a cipher, the same ideas apply, in the studies of random quantum circuits. If you use gates in U4 or O4, it's just the only difference is that there are different symmetry sectors in these different groups. But the take-home message from this slide is just to say that it is very similar for the different group elements. And what just changes is details, but you wouldn't expect that the time to equilibrate should change if you change the details of the gates. That should be universal. Now, if you take a given string, a given Pauli string, and you ask what happens when you conjugate by a gate, well, your wave function can spread to different string states, okay? And there are matrix elements for a finite number for a gate that acts on, say, either 2 qubits or 3 bits. And this is generically what happens if you take a random unitary or random permutation, litter permutation box, or U4. Now, an example where you don't have these proliferations, that a string doesn't go into many, it doesn't have amplitudes to go into many, it's more classical-like, if you wish, is if you take the linear gates in S8 or the Clifford gates, which is a subset of U4. In that case, you go from one string state to another string state, not a superposition, but it's one-to-one. So this is actually why it is possible to simulate Clifford gates in a classical computer, because you basically have a classical process. You have just these transitions, you don't spread out. Now, we can quantify how much you spread, how much entropy you generated by just taking each of the gates and computing, the rate of entropy production. And this is what I'm going to show next, but, it kind of like crowds the slide. But the bottom line is that for each set of gates, we can characterize how much entropy is produced if you take, for example, if you compute the average entropy averaged over the different gates, okay? And that quantifies that you're spreading in string space. But now with all this background, I'm going to come back to the question, why is it difficult to encrypt in time log n, right? Why is it that if I throw a circuit at random, random circuits done in the usual way will not do that. And the underlying reason is this, is that if you have L layers, right, think about L as time. If I start with a small Pauli string, like I flip one spin as a sigma x, as I evolve, I scatter into different string configurations, and they'll have different sizes. Like, well, if I have, under a unitary evolution, for example, I can only have weight 1 goes to 1 or 2 because I only have 2 sides. If I have a 3-bit gate, it can go to weight, 1, 2, and 3. But then if I follow this, and suppose I track the amplitude of having a weight 1, and I keep on looking at the probability of having a weight 1 string after L layers. Well, if there was a probability of staying at weight 1 after L log n times, I will get a power law tail that will have a small string. Okay, so there is a large probability, a power law in n, that my string, didn't grow right? It stayed small. And we can check it numerically. So, for example, what is plotted here is the number of bits that you flip on the output if you flip an input bit as a function of the number of layers. And if you look at the density plot in the bottom, like, and if I only plot the average, I would be happy. Oh, this just looks like all those curves that we plot in random quantum circuits, right? Oh, something saturates. And even if I look at the distribution here, well, it kind of looks Gaussian. So I'm happy, right? It's a small fluctuation around the average. So you really kind of, the number of bits flipped is like the size of the string. But the problem is that if I look at the tail, the probability that I have weight 1, it is decaying very slowly as a power law. So, and this is the problem. Okay, this is not good enough for crypto. Okay, maybe we don't bother if you say, well, yeah, it's a log n scrambler. So here the idea is that we want the best scramblers possible so that they're secure. But we want that log n time that one gets in the black hole or the random quantum circuits. So the solution is inflation, as in, but I hate to say this, but inflation, we're all suffering now, so it's not a good word to hear. And especially, I would say, like, when I grew up, inflation was really, really a big problem. But here, the inflation is used in a different meaning. So what we did is, like, we searched for a special set of gates. And I'm going to hit this key over and over that we will have to escape away from unstructured circuits, because otherwise you're going to fall in a trap of some universal behavior which will not give us this torus scrambling. So you can actually search and you find out of the permutation gates 144 gates that have the following property. In bit space, that's easier to see. And the same thing happens in string space. The string grows. In bit space, if you flip an input, you always flip 2 outputs independent of the state of the input. In string space, it means that if you have a weight 1 and you conjugate by this gate, you always go from 1 to 2. And if you structure the circuit as tree-like, because we want this tree-like, because tree-like is like infinite G, and we know from the arguments, right, of information spread in the from the black hole, from the quantum circuits, that we need basically to work in infinite G, and the tree is like infinite G. So if you do these 2 things, and we separate, we structure the circuit as having inflationary gates, which are linear, then we put the nonlinear gates, or even you throw all the universal gates here if you wish, and then you follow by another layer, we will take care of we will eliminate these issues with the short strings. Why? Because if you come with a short string, as you conjugate with these linear, these inflationary, they're going to be large and they're not going to have a tail. And you put on the both sides because you also want to that kind of time reversed. If you have an attack with a short string here, you want to blow the string. And these are the guys who generate entropy. So we need both of these things. We need to grow the strings and generate entropy. So if I use that structure, and you see that we basically eliminate the probability of the short strings. And if I take the cross section here and actually compare the speed at which you can say the string weights or the number of bits flipped grow, this is actually the maximum speed that you can attain. If I take circuits drawn uniformly over the whole set, I have a much slower speed than this. So the inflation really kind of blows up the strings as fast as possible. And then, and then things saturate. So again, compare these 2 here. You kill it and you never come back because you flip 1, you flip 2. The weight went to 2, from 2 to 4, 4 to 8. Now I'm going to get to this discussion about infinite Lyapunov exponents and why why we need it. So, like I said, the circuit is structured like a tree, so we can do kind of a mean field-like calculation where we can compute quantities like these OTOCs, and we can do average over circuits over a gate set. And we can also square and average. We can write these two quantities, like the Edwards-Anderson-like or just the average spin, average S. And then we write recursion relations that if we know what these quantities are after L layers of conjugation with the layers of the circuit, we can write a recursion relation for the L+1 layer, and they are written here. Now, I don't pay attention to details of the the entries in this equation. The only thing to notice is that if I look on the right, it's a series expansion, and the degree is depends on the number of bits in the gate. But think about it as a series. It's going to be a linear term, a quadratic term, a cubic term, and then there's going to be all sorts of cross and mixing. And if you ask if it's a series, and especially as these things, as these quantities S and Q become small, what really matters are the leading terms in the series, which I highlight in red here, which is linear for these nonlinear gates. And this is true also with just different coefficients. If you take the average over the whole set. So that's the universal behavior. You would expect that the series would start with lowest term. The inflationary gates, they're special is that you never have the linear term in either series, okay? So it is, you could ask, that's the defining property. You want gates such that they never lead to a linear term. And why does that matter? If I take the universal kind that in my series, I'm always going to be led by the linear term in the series with some coefficient. If I solve the recursion, okay, I get that the Q of L will be exponential. It will be that constant to the power L. And this constant is less than 1, so you're going to go exponentially in L to 0. You can think about this as giving you a finite Lyapunov exponent, and it will lead to a power law in N if L is log N. Now, what is special if you have a set that that coefficient in the linear term vanishes identically, and it has to vanish not just on the average, but for every gate in that gate set, it vanishes. Then you get a different recursion. You get a quadratic term. And when you solve this quadratic recursion, you get a double exponential in L, right? So the Q of L is decaying as a quantity raised to the power 2 to the L. Now, if L is log N, this is going to be N, and then you're going to see that you're decaying exponentially. So this is basically it's the reason why we need to separate the gate set, because we need to reach these kind of infinite Lyapunov exponents. And then you need the inflation, but you're also going to need the nonlinear gates in the middle because the linear gates don't generate entropy. So we check this numerically. As we compute this quantity, the kind of Edwards-Anderson like the square of the OTOC average. And as you go through the first linear layer, nothing happens because it's linear. Then you have this exponential decay after you go through the green layer. And then you have the double exponential decay that is so fast that it leaves the numerics behind because we only have 10 to the 8 samples here. And this is that idea that, if you want to tell whether this quantity is 0 or not, you can only do a certain number of computations. And here the computer is left behind, right? But this level I cannot distinguish, right? This is basically the how much you can distinguish, and the actual system is way below. some remarks on this decay of the OTOC. So we found that this does everything. It generates the entropy, it decays. But here's a warning, and this starts to be the point that we're gonna get the message and send across to the fundamental side. And usually we would think that the OTOC is a signature of chaos. But at least if I work on the classical circuits, I would argue that it's not sufficient. We also need the entropy. We need, because if I have only one layer of nonlinear gates sandwiched by these inflationary gates, you can show the OTOCs go to 0. But if I only have one layer of nonlinear gates, this function, the output function, is a second degree polynomial because the degree grows with the number of layers. So I can learn this function. So it's learning in the sense of computational learning theory. I can actually find out what is the, for any, if you give me the output, I can figure out what is the input. Certainly that wouldn't be a good cipher. But if the OTOC vanishes, I would be cautious and say, okay, well, is this really a signature of chaos? Because, it's completely predictable. Right? It's even if you change your, you flip the conditions here, I would know what to do. So it's just a warning. We would claim that you need also the string entropy to saturate to say the system's chaotic. And now, if I take, so we succeeded in building a cipher with log n layers, which is with the OTOCs saturating, exponentially small. Better than if you don't have structure in the random circuit, like the things that the black hole was compared to and the studies of the random quantum circuit. So now we can ask the question, can we extend what we did for classical circuits to quantum circuits? And so the answer is yes, because we do have the inflationary gates that we can just replace the S8 gates by U4 gates in the 2 qubits, but it still use the same inflationary gates that will blow the string that does the trick. Now, okay, I'm using these 3-bit gates inflationary. And the interesting thing is that, and it would actually tell us that if we only use 2 qubit gates, you would never be able to scramble to exponential precision because there are no 2 qubit Clifford gates. You can think about either you need 3-bit gates that are like put this in a box, or you need structured 2 qubit gates to get this result. This is an argument from a former student that when he saw this, he said, "Oh yeah, one can argue that if you take a weight 1 string that maps into a weight 2 for both the x and the z and the y, you hit a contradiction." Okay, I won't go through all the details, but he showed it's very simple that if this is true for x, y, and z, you're going to have a problem with the commutators. Okay, so this shows that you can't build inflationary gates out of 2 qubit gates. So that would explain why, even if we want tried, like you need to put this structure. So I think I'm going over time.
Right. I wanted to remind you about the time and how much time do you still need?
Yeah. So maybe I think I can wrap it up in maybe 5 minutes or less. I just want to go back to this question about the encrypted operator computing and why, this log n ciphers would be important. How actually one can construct the argument. That's not quite how we do it, but it shines light on how. So let me use a simple example. Suppose that the function that you want to compute is the identity. So clearly this is trivial. If I have E inverse and E, I can completely hide the contents of the gate set of the E. So all the information is erased. And I could even see this if I expand my circuit gate by gate, because gate by gate, they annihilate. Now that's too trivial. Now suppose that you start going a non-trivial example. What if I put a knot? Well, again, we only draw things in 1D here because it's easier to draw. but there will be the states, in the dark region outside the light cone and the stuff in the light cone. Whatever is in the dark region is just going to annihilate. But one could imagine that, oh, you're keeping information about what's in the light cone. That's not quite true. You can argue that there's still information erasure. It's not as complete as in the dark region. As a simple example, if I have these two gates, if I don't know what is G inverse and G, I can put, for example, a random knot here, absorb it here, absorb it there. I don't know which gate there is. I could do swaps and, basically what I'm trying to say is that if you multiply these gates, it becomes very hard to factor back into the original form, and it's not unique. Now, you can do this, a 3-bit equivalent, and I ate up a layer. And then I can eat up the next layer and write a bigger circuit that then you factorize into 3-bit gates. And there's exponentially many ways to factorize. So if I keep on doing this, multiply, build a bigger block and factorize back into 3 and keep on doing recursively, what happens is that at each level in the recursion, the number of gates goes by a factor of k. And if you have L layers, you have k to the L. So here we go back to why it is so important to have a cipher with log n layers, so that this can remain polynomial. So this is just an argument, because actually in practice, what we like to do is you also matters how large k is, because practice is different. Like computer science, a theoretical one would say, well, it's a polynomial, I'm happy with that. But in practice, we want to decrease the exponent. And if we succeed on that, of scrambling the circuit, not scrambling the states, a new, it's kind of a new step, right? There's a lot of maybe 15 years of studies or more of random quantum circuits, Now, what about scrambling states? Now we have to scramble circuits. But if this succeeds, then when we have an application such as machine learning and encrypted data, going back to that motivating example. So in conclusions, we present a framework for analysis and design of classical ciphers based on a very close conceptual connection to the problem of scrambling quantum states. And these parallels, they emerge very naturally if we just start translating, that language of, attacks, differential attacks, linear attacks, all these things in terms of OTOCs. And then we argue that to reach we can do this in log n, but we need to meet a higher standard than what was asked of the black holes and random quantum circuits. We actually have these OTOCs to vanish exponentially. And that it is only possible if you structure your circuit. If you have a homogeneous circuit drawn uniformly at random from your universal set of gates, you wouldn't hit, you would scramble, but to a polynomial precision, not an exponential. And the result should carry to quantum circuits. And that, again, so the upshot is that by structuring, I don't know if the black hole is structured, but the quantum circuit you can structure. And we can scramble as fast as, but to a, much higher standard. Whether this has an application or to black holes, or if it's important to scramble to that degree of precision or not, remains to be addressed. And perhaps what I would single out as the most important, and going back to the applied side, is that that depth may allow us to construct this physics-inspired approach to computation on encrypted data. And thank you for your attention.
Thank you very much, Claudio, for this very interesting talk. And now we can pass to questions. Let's see if there are any questions. I may start with the question, and I would like to maybe compare what you talked, this inflationary circuits in particular, with systems. Well, if we can see the circuit as a conductor, or some quantum material, it looks to me that I can make an analogy that the fastest, the inflationary circuit would be the one which corresponds to some kind of isolator, while the normal random circuits, they are more like a critical. They're more at critical points, so close to conducting point. So I'm not sure that this is the correct analogy.
Yeah, Nancy, it's yeah. Maybe I'm gonna go back to the defining property here that you use. If you have a universal gate, when you conjugate that information, in a way, it propagates more mildly, even though you spread in different amplitudes. But you are spreading it more continuously, right? Whereas this guy, because you flip, you have this cascade, right? The information never comes back. So in that sense, you can think about it's more like a diode, right? Like in an insulator, right? It's something that goes one way, that it doesn't. Yeah, in the street propagates. Now, let me mention one thing that even though we have this idea that you flip one and it propagates, you could ask, what about the time reversed version? Because the inverse inflationary gate is also inflationary. So you could imagine a situation that if you run things backwards, you start with a large string that focuses it into a single string. But the thing with that one is that it's exponentially hard to find that string, right? Because the string has a lot of weight. It touches all the bits, right? So how do I know if I'm going to place a sigma x, sigma y, or sigma z at that site? And I have n of them, so I have like 4 to the n possible strings to choose, and there's a handful of those, like order n, that will refocus. So because of this difficulty of finding the strings that refocus, and because the attacks are usually done with you can choose a couple to flip, but you cannot flip an arbitrary string. You can, but you have to find which one. So in that sense, going back to your insulator, that's isolator. It is a bit like this, right? That in the input and the output, I kind of at the two ends of this inflationary stage, I have this circuit element that the effect is just to blow up in one direction, and it's really hard to invert it. I don't know if kind of my analogy helps with your analogy, like if they match.
Yeah, I'm not sure that my analogy also was a good analogy, but I think you sort of you see it differently for sure. Maybe let me use this opportunity and ask, because I'm not sure I understood what exactly are the inflationary gates. What do they do? How you distinguish them from
okay, so
gates?
The defining property is that first of all, they're linear in the sense that they do not proliferate the number of strings. If I conjugate a Pauli, I'm just going to get another Pauli. Let me just go back to a generic gate will spread your string. The Clifford and these linear gates, linear classical gates, they have the property that it takes one string of Paulis to another. So so the inflationary gates are linear, so they take one string to another. But they have this property that when, in string space, when I conjugate a string of weight 1, you always go to weight 2. I'm going to go all the way to the writing them in terms of C-naughts. So maybe let me take this one here to show how they work in the setting of a quantum circuit. So suppose I have an input. If I flip this bit, okay, irrespective if this control is, in the language of quantum gates, like C0 has a control that's a white dot or a black dot. If I flip this bit's gonna flip this one as well, because if the C0 was inactive, it becomes active and vice versa. And then because I flip this one, I will flip this one as well. Now this one may flip the first one back, but what happened is that by flipping this bit, I end up flipping these two. So what the inflationary gates are, they have this property that if you flip a bit, they will always, with a probability 1, will flip 2 or more. So they have this property of, it's an avalanche. And yeah, so that is the defining property, is basically that conjugate, it blows a string so that you're guaranteed that the evolution in string space will bring you to large strings.
Yeah, I guess that's a natural interpretation. When you mentioned inflation first, of course, I thought of cosmological inflation. So that's what they're trying to do here.
Yeah,
but it looks to me a little bit like, okay, that's an accident because we're using C0 gates, and then they have this property. I'm not sure if you can give a more general definition of, or how do you know like which gate I should use?
Okay, I can give. For example, when we found them, actually we didn't find them in bit space. We found them in string space. So the criteria would be, and then you could generalize for, if you're looking for inflationary gates in n, say n bits or qubits. You could basically, out of the gate set that you have, and suppose that you have a list there, they would be countable. And you list all possible gates, and now I look at the matrix elements and ask that the amplitude to go from 1 to 1 so that it stays. I want it to vanish. And I can go just through that list of gates and toss out. So that's how we actually found these inflationary gates. More recently, we actually found that we could count them in different ways, right? That was actually this thing about the in bit space. But if you ask, could we find inflationary gates on using 4 qubits? Then we would have a prescription of how to do it. Right?
I see. Yeah, thank you. So there's a question from Fabio. Fabio, please go ahead if you can unmute yourself. Ask the question.
Right. Thank you for the word. Right, Claudio, beautiful talk. Many new physical concepts. Right, rich physics. Look, in some moment you showed in your slide that the mathematical tool OTOs is the correct tool to characterize the chaotic regime. And with this mathematical tool, you could realize 2 kinds of Lyapunov exponents. But as you said, also one physical variable to analyze is the entropy as the state function of the system, right?
Right.
Look, in this fundamental side, how can you, by means of the entropy, you can figure out these 2 kinds of regimes in the Lyapunov exponent, if possible? And if no, what kind of more physical analysis you can do to realize the chaotic regime in your system?
That's a very good question. So I'm going to go back to this example of the entropy. What we did the analysis in the OTOs, the decays, to show that we get this double exponential. We needed this the evolution through these inflationary layers, but they don't generate entropy. So actually, I'm going to go back, and this is even showing them here. So as we evolve past the inflationary layers, because they're linear, they don't generate entropy in string space. And the reason is that you take one string configuration, and as you evolve with them, you just move the string from one configuration to another, but it's always one-to-one. So when you compute the entropy, it's always zero. So we wouldn't know how to characterize yet, right? It's a very good question. Can we understand, the Lyapunov exponents through the entropy? At this point, I don't see how, because since these gates are linear, they don't generate entropy. It's almost like you have to make these good ciphers. You have to separate the process of entropy production from the blowing the strings. Blowing the strings, and when you combine both is when you actually get the DOC to decay. For example, let me give an example. Unless we have even a single layer of the nonlinear gates, you cannot seed the decay, this double exponential decay. So you need the Q0. So suppose that, let me take the C to be 1 here, because, well, it wasn't quite 1, but 1 is a fixed point of these equations. So unless I have some initial decay due to the nonlinear ones that generate the entropy, the OTOC will decay. So it's a combination of both. You need the entropy production, and you need the mechanism to blow the strings to get the OTOC. In the cipher design language, people way back when, even in the dates of Shannon was the one who proposed these ideas of diffusion and confusion. So this was, I think, maybe in the 40s or not much later. So the generation of the entropy is like the confusion, and these guys are responsible for the diffusion. But early on, they realized that you need to separate these processes. And in the study of the random quantum circuits, we're not separating them. We're trying to get something to do both. So if I go back to your question about can we detect these exponents from the entropy, actually, this would be a counterexample that I don't think we have enough entropy, but we do have a saturated DOTOC, and consistent with these infinite Lyapunov exponents. So it's a good question. I don't know how best addressed, but I think that it is possible. I don't see how to connect the entropy from what we have to the Lyapunov exponents. With this being actually a counterexample, we still have the infinite Lyapunov exponents, an extensive entropy, but not saturated.
All right. Claudio, thank you for your gentle attention and good explanations too. Congratulations.
All right, thank you.
So just to clarify, following Fabio's question, so when you talked in the beginning, systems that do perform better than black holes and scrambling information. So this is what you mean. You have systems which produce entropy, and this makes it well, was it the OTOC that decays exponentially, or
it's the OTOC that decays exponentially? So if I use that as a criterion, like let me put the black hole and the random quantum circuit on par, because in the absence of any other structure inside, like a structure like these 3 stages. So what I can say is that for the random quantum circuit, you wouldn't be able to suppress the OTOC exponentially in N if the circuit is not structured. So that would be the precise statement. That.
Thank you. There's one more question from Tiago. Tiago, please.
Thanks, Claudio, for the talk. I think it's a simple question. I didn't understand well that argument by Young. What is the? It's a follow-up by Dimitri's question about the definition of inflationary. Oh, you got a contradiction of there? Or
say it again. Which contradiction you mean?
No, that argument that you mentioned that it's not possible to generate with two Clifford inflationary gates. That argument by Young.
Okay. Okay, so the argument would go like this. So suppose it's true, and this dot and the star just means I don't know if it's X, Y, or Z here, but I just care that there is a Pauling in site 1 and a Pauling in site 2.
Okay.
So I know that the conjugation doesn't change the commutation relation. So these two anti-commute. So these two operators should anti-commute. So if they anti-commute, and I have an operator in site 1 and 2 for both, the only way for them to anti-commute is that one of the dot here and the square have to be the same, X, Y, or Z, and the other one different, or vice versa. Because otherwise, if the dot and the square are different, and the star and the diamond here is different, then they would commute. So, but if this is true, if one of these are equal, when I multiply them together, which will give us the sigma y, say these two have the same coordinate. When I multiply, they will cancel. So that will give me a weight 1 string, not a weight 2. So that would be the contradiction, that you cannot have a 2-qubit gate that takes always takes a weight 1 to a weight 2. So and that's why I would say like a little.
But for more than 2 bits, it's always, is there any special number of qubits that you can also do some argument that is nothing, or every number bigger than 2?
I think every number bigger than 2, and probably like the problem is it's a little space too. You're kind of like too stricted. So you see that through these two had to be equal in this argument. But I think if you have 3, you have more space to preserve the anti-commutation, right? Because you don't have so many commutation rules, but now you have more space. Yeah.
Okay.
The other option, and we've been thinking about it, is what if you, instead of having qubits, you have qudits? Is it possible to have a 2-qubit gate that inflates? Because now, say, if you use, instead of U2 gates, or U4, you use if you have 3 states, right? You would have, instead of Pauli matrices, you would have Gell-Mann matrices. Maybe now you have more space to design inflationary gates with only 2 qubit gates. So that's an interesting possibility we're going to be looking at.
Okay, thank you.
Okay.
All right. Thank you, everybody. Thank you, first of all, Claudio, for this great talk. And I thank everybody who participated. And I would like to announce that was the last virtual seminar of the International Institute of Physics this season. And thank you, everybody who participated in our seminars. And this year we had really a very interesting set of talks and very interesting speakers. Soon the feast of international football will start, and in Brazil, football is more than just soccer. So we wish everybody and Brazilian team the best success at the World Cup, and I think we all will support, including Pasquale, who has, I'm sure he has a yellow shirt in his closet. Okay, thank you very much. Take
Please
care.
don't make it
Okay,
so.
thank you, everyone.
Okay.
Thank
Ciao.
you. Thank you, everybody.
Ciao,
Bye
ciao.
bye. All the best.